Start our seminar. It's our first in-person seminar this semester. Last semester, only one seminar was in person, done by Mark Blyth. Dedicated to him. And today we kind of, it's a first step returning to normal in some sense, and the step will be done by Blyth. My congratulations to Mark with the higher position he's going to get from August.
Thank you.
And okay, it's not inaugural lecture, but again, could be first step to that. So we should speak there. Okay, because this is the in person, but also online. So the people like John Ockenden, John, I believe you can see us and hear us. But all microphones should be muted. Also, it's recorded and it will be on YouTube. Yeah, so they say in once, and Mark, it's yours.
Thank you, Sasha. Thanks very much for coming, everybody. It's really nice to be back in this room to start with. After more than 2 years, it seems a bit strange, but it's really nice, and it's really nice to do this in person. So what I'm going to, so I have to try and remember to stand here, I guess, so you can hear me.
No idea.
Okay. What I'm going to talk about today is some work that Emilian and I did with a PhD student who graduated. Actually, I completely lost track of when he graduated, 2 years ago or something. Adam Yorkston. So everything I'm going to talk about was done by Adam. He did some really, really nice work. And what we were trying to do was start to think about how you would model a deformable aerofoil. So the emphasis in the title is on the first word. Okay, I'm not claiming that this is going to be enormously realistic, and certainly at the beginning it's going to be highly idealized, and we'll start to make it slightly less so by the end of the talk. Okay, so please keep in mind this first word, that's the direction we're heading in. Okay, so as I said, this was work done with Adam. Adam has unfortunately left academia now and is working in insurance. But it was a delight to work with him for 3 years and with Emilian on this work. Okay, so why might we want to have deformable aerofoils? Well, first of all, these occur in nature. So this is a picture of a dragonfly. So their wings, there's some rigidity to the wing, so there's some structure to it, but also some leeway to deform and change shape to some extent, presumably for aerodynamic purposes, for efficiency and so on. So we see these things in nature, and we might want to try and mimic that. So here is what's known as an unmanned aerial vehicle. So I guess there are lots of reasons why you might want these things. So I think the size of this thing is sort of something like this. You can pick up and hold, and this one is entirely inflatable. I think there might be a bit of a rigid structure to it. And here's another example of an inflatable drone. So you can see what the size of that thing is from the people standing in the picture. These things typically go at about 20 to 30 miles an hour, something like that. That's about the normal cruising speed, although this one we're looking at can go up to about 120 miles an hour. So there is some variability in the speeds at which these things can fly, and I've tried to list here some of the advantages of these. I haven't bothered with the disadvantages, just the advantages. So they're light, they're durable, so if they hit the ground, then they may be more likely to survive the impact than a rigid structure. You can land on water easily. They're portable, so that's one of the key advantages. But I think that probably what people are most interested in is the bottom one, at least in terms of trying to create aeroplanes that can deform their shape in mid-flight. They can then change the mode of flying from one thing to another. For example, just cruising at a steady altitude or undertaking tight maneuvers. You can switch the capability of the aircraft from one to the other, possibly. So this doesn't exist at the moment, at least for something like this inflatable thing. But that might be the idea. Okay, and there's a nice review article, by the way, if you're interested in this stuff, published fairly recently, discussing some of the things I've been talking about in more detail. Right, so I said we'd start highly idealized, and this is where we begin. So what I want to think about is an elastic cell, and when I say cell, what I mean is, so where is the cell in this picture? It is, what you're looking at here is an inviscid, as the streamline pattern suggests, an inviscid incompressible irrotational flow going, well, let's say from left to right, past an elastic cell, which is this, this shape here. And by cell, I mean it's got a thin wall made of an elastic material which can deform and change shape. And when it does that, it develops elastic tensions and stresses in the wall. And then inside the cell is another fluid which is just held at constant pressure. Okay, so there may be some pressure difference between, let's say, infinity over here and the interior of the cell that wants to make the cell deform. And also there is a flow, as I've shown you there, that's imposing a pressure on the boundary, which is not obvious what that pressure force is in advance until you solve the problem. That's the basic idea. And the question then is, what shape does the cell adopt when you put it into this flow, given that it can deform? Well, perhaps the closest work you can think of to this is if it wasn't an elastic cell, but it was a bubble, for example, and you put a bubble into the same flow, then what happens? Well, this problem was looked at by Jean-Marc van den Broek, who used to be here, of course, and Joe Keller in 1980, and then subsequently by Shankar and Tanveer in the 90s, and Ni and Tanveer looked at the stability of the bubble shapes that occur. But essentially what happens, what you're looking at here is the top half of the bubble that's been placed into a flow which is going, again, let's say from left to right, for various values of the relevant dimensionless parameter. And what happens is the bubble starts out circular, and then the flow comes towards it, and it starts to elongate in a direction perpendicular to the flow. Okay, and eventually it keeps elongating, and as it elongates, it kind of pinches together at the middle, and if you push it hard enough, eventually it will pinch together and develop a point of contact, and then the bubble will presumably break up thereafter. So that's a bubble in flow. What about an elastic cell? Well, let's go in small steps first and think about an elastic cell that's not in a flow, it's just in a static fluid, that's where there's a pressure difference between the outside of the cell and the interior. So this is a classic problem that's been looked at for many, many years, going back, I think this is the first relevant work in 1884, and then various authors have looked at this. These figures here are taken from the paper by Flaherty et al. I think Joe Keller is again an author, he's one of the et al. In here, I think, from 1972. So this cell starts out as a circle, and then the pressure differential between outside and inside is increased. And as it's increased, the thing starts to buckle. Right along the bottom. So it buckles into what we might call a mode 2 shape here. And then if you keep driving up the pressure difference, eventually something similar will happen to what happened with that bubble a minute ago, and a point of contact will be established. And then what they did actually in this paper was take it even further and allow the pressure to increase, so the point of contact stretches out into a line of contact. So there's a whole segment of the elastic cell which has been pinched together with two little bubbles, if you like, above and below. So that's a static cell with no flow. Okay, so if we begin to think about writing down some mathematics for this situation, the first thing we want to know is what's the force balance on the wall of the cell. So if we take a little segment of the cell, okay, so that's a little segment of length ds, say, and then think about what the force balance is across that. So the forces active here are P of S is arc length, right? So the pressure in general will depend on position once this thing's been put into a flow. If it's in a static fluid like the Flaherty problem, the pressure is just a constant. When you put it into a flow, it's going to depend on position. So P will depend on S. The cell wall is made of some material which has some density and therefore has some weight associated with it. Little rho c is going to denote the density of the cell wall material. Okay, Okay, and later rho is just going to be the density of the fluid that we're putting this thing into. So the forces here are the pressure, there's the weight of the portion of the segment, and then there is a tension, capital T, a normal force, capital N, and a bending moment, capital M. And what I've written down immediately below is the force balance over that segment of length, or I guess it's of length 2ds, the way I've written it. If we take the limit as ds goes to 0, we get this differential equation expressing the force balance on that on the wall. Taking that differential, so there was a d by ds, let's just skip back a second, there's a d by ds there. When you take that d by ds into the bracket, you're going to start differentiating. So n hat and t hat are the normal vector and the vector tangent to the boundary representing the wall. When you differentiate those unit vectors, the curvature of the cell wall is going to come in. So that's what's happening on the next slide. So little kappa here is the curvature. And all those terms in that force balance are represented in terms of the direction n hat, normal to the wall, and t hat, tangent to the wall. Okay, kappa is the curvature, as they say. Oh, another thing I should make really clear at the beginning, it's not the beginning anymore, but I would have done if this was the beginning, is that everything is going to be 2D. Okay, so there's another simplification we're making. Everything I'll talk about today is in 2 dimensions. Okay, so force balance. We also need a balance of moments. That leads us to this conclusion that the normal force capital N is so the subscript there is a partial derivative, is dm by ds, s being arc length around the boundary. We will need a constitutive equation which relates the bending moment to the curvature. Now, everything I'm going to talk about this afternoon will assume that the cell is inextensible. Okay, it cannot be stretched. Although actually the only point you need to invoke that condition mathematically is in the equation at the bottom that says that the bending moment is linearly proportional to the curvature. Okay. So if we take components in the tangent and the normal direction, these are my 2 force balance equations. And the unknown in there, or the key unknown, is the pressure P of S. We get that from shoving this thing into a flow, calculating the pressure around the boundary. That gives me P. I can then solve the shape. And then I guess there's some iteration to be done to get these things to agree. Right. That equation for the tangential balance, if you look at it for a moment or two, you see that I can integrate every term through the equation with respect to S. And if you do that, you introduce a little constant of integration sigma. So this is going to appear over subsequent slides. So that's a constant of integration, and that's fixed essentially by requiring that this cell is closed so that it forms a closed contour. Okay, that's how that constant of integration gets fixed. You can eliminate capital T completely to get an equation there which only involves the curvature, kappa, and its derivatives, the pressure, and this constant of integration, sigma, as well as the weight contribution through rho c. So it's that equation I want to solve for the shape of the cell, and at the same time, I want to solve the equations of fluid motion outside the cell to give me the pressure. Okay, so if we go back to the Flaherty problem, let's knock out gravity now. Okay, so let's say that the cell has 0 mass, or there's no gravity. Then the equation on the previous slide under that, if you knock out gravity, reduces to that one at the top. And if we solve that, we get these solutions from Flaherty's paper that I showed you a minute ago.
Mark, let me ask you, how is possible that the shape is symmetric? You fix it, or?
No, so the symmetry appears naturally. Can you hear me? Oh, okay. So the question was, why are the cell shapes symmetric? Yeah. So,
because it's in the flow, right?
No, these are static. There's no flow.
Why is it change shape? For the pressure?
Yes, there's the pressure differential between the outside and the inside. So one solution to the problem is always a circular cell. But when the pressure, so I'll talk about this in a bit. When the pressure differential exceeds a certain value, then the circular cell is still a solution, but it loses stability and the thing wants to buckle. And it can buckle into a mode 2 shape, which is what we're looking at here, or if the pressure goes higher, go to a mode 3 shape with 3-fold rotational symmetry and so on. Okay. Right, okay, so now let's take that cell and put it into a flow, which is what we wanted to do. So we'll assume we've got far enough to the left, a uniform stream with strength capital U and pressure P infinity coming towards our cell, negotiating its way around the cell and then going off to the right. And what I want to know is, what do the streamlines look like? What pressure does that impose on the cell boundary? And what is the shape of the cell? So the way we can address that problem, the way we're going to do it, is via complex analysis by introducing a complex potential and then using a conformal mapping. So little w here is my complex potential. So if anybody's not seen this before, it's simply a device of, you invent this function w, which is an analytic function of z, and it turns out that if you differentiate w with respect to z, you get little u, the velocity in the horizontal direction, minus little iv, where v is the velocity in the vertical direction. And done, you've solved for the flow. Okay, what are the boundary conditions? Well, at the cell wall, we'll have a kinematic condition. Now, most of what I'm going to talk about today is steady, although I will show some unsteady simulations. But the kinematic condition would say that if eta represents a point on my boundary, then the motion in the normal direction should fit with the component of velocity in the normal direction. And if we express that in terms of my complex potential, it takes the form of this equation here, which is not obvious. Okay, but that's just what it looks like. So eta here represents the cell wall with some parameter phi just describing a point on the wall, and t here being time. So in the far field, we've got a uniform stream. So as z goes to infinity, w approaches a uniform stream, that's this uz term. And I also want to allow there to be some circulation, because I want this to be an aerofoil ultimately with some lift on it. So capital gamma is the circulation, and therefore I include this point vortex term, which is the second term on the right-hand side there, where capital gamma is the circulation. Okay, that's what that's doing there, so we can have lift. Well, if you do that, then the flow at infinity, because there's no source term at infinity, then the area inside the cell must be conserved. And you can check that. So a nice little exercise with the divergence theorem tells you that I can express the area inside the cell as that integral. And then if you differentiate that with respect to time and use the kinematic condition from a couple of slides ago, after a little bit of work, you can show that dA by dt is equal to naught, as you would expect. Okay, so not only is the cell perimeter going to be conserved in what I'm describing, but the area inside the cell is also fixed. Okay, so as I said, you need an extensibility to get the constitutive relation between the bending moment and the curvature, and then we're going to fix the perimeter to be capital L. Okay, so from now on, capital L is the perimeter of the cell, and as the cell deforms, it doesn't stretch, so it doesn't change its length. Now, in introducing this circulation for the relevant calculations when we have circulation, I'm going to assume that we've got an aerofoil or an elastic cell that's cruising at a constant altitude in some equilibrium where any lift that's induced on the aerofoil is perfectly balanced by the weight. Okay, so the lift from the Kutta-Joukowski theorem is given by minus rho. So rho here is the density of the air outside the cell. So the Kutta-Joukowski theorem gives me the lift as minus rho u capital gamma. Capital gamma is negative, so that's an upwards force. And then we've got the weight downwards, rho c gl, and those two things are assumed to be in balance. And we'll assume that that works by choosing rho c so that it works. Okay, so I'm just going to choose the density of my material so that these forces balance and the thing can just cruise at an equilibrium height. Effectively, what I want to do is calculate steady solutions where the cell is not changing shape in time. So that's why I'm setting it up like this. I'm also going to assume that the density of the fluid outside the cell is the same as the density of the fluid inside. Now, what our idea here was that we could kind of model the architecture of the aerofoil or the machinery and whatnot of an aeroplane inside this aerofoil by another fluid. This was kind of the way we were thinking here, by fixing the density of the interior fluid to kind of model the weight of the aircraft. But in these calculations, I'm just going to set those densities equal, okay, to keep things simple. Right, okay, so there's the basic setup of the problem. There are three dimensionless parameters that we can play with. The first one, which I'm going to call alpha, is effectively the speed of the oncoming flow. Okay, so if alpha is 0, and we'll take it to be 0 shortly, then there is no flow. We're back to the Flaherty problem. Beta is the circulation. So if beta is 0, there's no lift. And P is the pressure differential between the pressure at infinity a long way from the aerofoil and the pressure inside, little p0. Okay, so three dimensionless parameters that we can play with. And EB, I don't think I've mentioned yet, is just the elastic modulus, a measure of how of the resistance of this cell wall to bending. So I said we'll use a conformal mapping. This is essentially following what Shankar did in 1992, and Tanvir did something similar. We introduce a conformal mapping and map whatever the cell shape is that we don't know in advance into the unit circle in the zeta plane via the mapping given below. So it's in terms of an infinite expansion in inverse powers of zeta. And what you want to know in order to get the shape of the cell are these coefficients an. So these are the things that you're trying to calculate. And the way you calculate them is by enforcing the boundary conditions. That gives you these coefficients. Once you've got those, you can work out the shape. So that's the dynamic boundary condition that we worked towards before. So you recognize perhaps the KSS term at the front. If you get rid of everything after the fourth term, that's the Flaherty problem. But encoded within there, there's an alpha squared. So the flow is encapsulated in that equation. There's a beta, so the circulation is there as well. So that's the dynamic boundary condition to be satisfied at the surface of the cell wall. By satisfying, in order to satisfy that boundary condition, I choose my ANs for my conformal mapping. Once I've done that, and the kinematic condition as well. Once I've done that, I've solved the problem. And then I know the cell shape, and I know the flow outside it as well. If we get rid of circulation to start with, and simultaneously forget about the weight, so knock gravity out as well, and the equation simplifies a little bit. We set beta to 0 effectively. And then if we get rid of the flow as well, by setting alpha to 0, and we go back to the Flaherty problem, then this now, Sasha, is your question from earlier, then this is what happens. So there's no flow now, nothing. We've just got a static cell, constant pressure outside, constant pressure inside. I want to solve that equation for kappa. Sigma is this constant of integration that I mentioned earlier. So it turns out that the solutions to this problem are that the cell can be perfectly circular, and that's always a solution. But when you increase capital P, so that's the pressure difference between the outside and the inside. So increasing capital P means the pressure is getting larger on the outside. So the cell is being pressurized from the exterior. When you increase P beyond a threshold, and that threshold, in fact, a sequence of thresholds given by n squared minus 1, where n is the natural number, 2, 3, 4, and so on. So the first one is 4 squared minus 1 equals 3. When you go past these threshold pressures, that circular cell solution loses stability, and the cell wants to buckle into one of these shapes that I showed you before. And if you keep going, so for example, supposing you push P beyond 3 and the circle buckles into a mode 2 shape, or a shape with twofold rotational symmetry, you keep increasing the pressure, what will happen is it's like that bubble from before. It will squeeze together in the middle and establish eventually a point of contact. And those points of contact for mode 2, 3, and 4 shapes are just given at the bottom there. Let me show you in pictures. So that's like the pre-buckling state of affairs, a circular cell, so capital P is less than 3. Then P goes beyond 3 and the thing starts to buckle into a shape with twofold rotational symmetry. And you push it hard enough so that P goes to 5 points, and this is calculated numerically, obviously, that value. Then you get a point of contact, and it was at this point that Flaherty continued their solutions by allowing that point of contact to extend out into a line. Alternatively, beyond P equals 8, buckled shapes with threefold rotational symmetry are possible that look like that. And if you keep cranking up the pressure beyond that value, eventually you get 3 points of contact like that at 21.65. And I think I showed fourfold as well. There we go. So beyond 15, so that's 4 squared minus 1, being the critical pressure this time, you get buckled shapes of 4-fold rotational symmetry. And if you increase the pressure far enough, you get 4 points of contact at points around the boundary. Right, okay. So the whole point of doing this is to have some flow, and I keep talking about static conditions. Supposing we take that circular cell and we just slowly increase the flow, okay? So the flow is encapsulated in this parameter alpha. So what I'm going to allow to happen now is that alpha become non-zero but small. And I'm going to take the circular shape, which it's set up so that the curvature of that circle is -1. Okay, so a circle has constant curvature, and we've just defined it to be -1. And then we perturb about that by these expansions here. Sigma is that constant of integration. Q here is the flow speed. Okay, so the modulus of the speed squared. For a circle, so for a uniform stream going past a circle, you can look this up in Bachelor, for example. Q is not just the square of the velocity; it's the slip velocity around the boundary. So if you look up in Bachelor, flow past a circle, the slip velocity is given by this, where s is arc length around the boundary. So we've got flow past a circular cell, and that circle wants to deform into some shape in response to this flow, and I'm trying to capture that through this expansion. So essentially what I want to know is what is kappa 1, because that gives me the deformed curvature. Okay, well, the reason for showing you this is that something interesting happens at a critical pressure. So if you substitute those expansions into the equation, so allowing weak flow, no circulation, so no gravity, but just weak flow, you substitute them into the equation, the order alpha squared, so at first order you get that equation for kappa. This cos 2s term on the right-hand side comes from that sine s term on the previous slide, which was the slip velocity around the circular undeformed boundary. Now, what's interesting about that ODE, I've shown it again at the top there, is that something is going to happen when P is equal to 3. Now, remember, P equals 3 was the first buckling pressure from the Flaherty problem. When P is 3, the coefficient of kappa 1, which is my perturbation to the curvature in response to the flow, the coefficient of kappa 1 is going to become 4, and then cos 2s is going to be one of the linearly independent solutions to the homogeneous form of that equation. And that's going to resonate with the cos 2s on the right-hand side. In other words, at P equals 3, there's going to be a resonance in this equation. Now, this is supposed to describe a closed cell. Kappa 1 is supposed to be the curvature of a cell that is a closed contour. So kappa 1 must be described as a periodic function. It must be a periodic function of s. At P equals 3, that resonance between the cos 2s on the right and the solution to the homogeneous problem is going to create non-periodic solutions. So what does that mean? It means the expansion is not going to work at that particular pressure. So this little calculation reveals that P equals 3 is not only important in the static problem, but in the problem with flow, it's also important because it creates some sort of resonance between the flow outside and the buckling pressure for the elastic cell. Okay, now what do you do about that? Well, in a couple of slides ago, what I did was expand in integer powers of alpha. You can get around this problem with resonance by expanding in fractional powers of alpha. And I don't want to go into the details, but let's just give you a flavor of how this works. If I modify my expansion to be in fractional powers that are thirds, then we can get this to work by recalling this trigonometric identity here. The important bit here is that if you cube cos, you get cos back again. So if I do cos 2s cubed, I get another cos 2s back. So the idea here is that if I expand like this, at leading order, my kappa 1 equation, I think I'll write this down next. My kappa 1 equation is going to be the equation I had before that had this problematic resonance in, but with a 0 on the right-hand side. So the complementary function will look like that for kappa 1. Then by the time you get to third order, which is alpha squared, it's at that order that that problematic cos 2s forcing term will come in my ODE. But at that stage, with this new expansion, at order alpha squared, I will get a kappa 1 coming in because of that cubed term in the equation at the top. There's a kappa cubed. And if I cube alpha 2/3, I get alpha squared. So kappa 1 cubed will come in at this order. But kappa 1's got a cos 2s in it. If I cube that, I get another cos 2s. So the summary of this is, if you do that, when you get to order alpha squared, the cos 2s that was messing up things can be eliminated through this one by choosing alpha 1 carefully, and indeed beta 1. Not alpha, sorry, A1 and B1. So that's exactly what you do. You go to order alpha squared, and you get rid of these secular terms which are problematic at this resonant pressure by choosing A1 and B1 appropriately. Now, what's interesting about this, so now let's go to numerical calculations via that conformal mapping that I showed you before. For the bubble problem, as I said right at the beginning, if you put a bubble into a uniform stream, it will start to deform by extending upwards in a direction perpendicular to the oncoming stream. If it's an elastic cell, it can do that, it can extend like that, but it can also extend in the direction of the stream. And which it does depends on what the pressure differential is between the interior and the exterior, and whether that is above or below that critical pressure, P equals 3. So the left-hand side here is for P equals 2, that's less than 3. And you can just about see that so the bubble was circular, not bubble, the cell was circular before it was put in the flow, and it's been elongated in a direction at 90 degrees to the flow. When P is 4 above 3, it's been elongated in a direction aligned with the flow. So that's an interesting difference between the elastic cell problem and the bubble problem. That its response to the flow changes qualitatively depending on the pressure differential. You can get mode 3 shapes in a flow as well. So this looks like one of the buckled mode 3 shapes from Flaherty, but this is inside a flow, so these are the streamlines of the flow. And I think what's interesting about this result is the picture on the right-hand side. That it seems perhaps intuitively reasonable that you might get a solution with a flow going from left to right that's top-down symmetric like that. But you can have solutions like this, where there is a top-down asymmetry with the fluid coming from left to right. Okay, those are steady solutions. I said most of what I want to show you is steady. Just for fun, let me show you what happens if you perturb one of those mode 2 shapes. And well, we did this to try and decide whether these things were stable. If you perturb them and look at the unsteady evolution of your perturbation, you get some quite fun results. So I'll show you a little moving. So we take one of these elongated cells, put it into a flow, and let it evolve in time. So this is done at each time step by solving that conformal mapping. And this is what happens. For a little while, it looks like nothing much is going to happen. The video is the top left bit. I have to exit full screen, do I? Can it be seen now? Okay. Try that one. There we go. So it kind of sits there, and then it sort of flips over, and then it kind of sits there again. It kind of flips over again, and it kind of continues with this sort of like almost like a sort of jumping beam or a rolling beam. And as it sits there, notice it's not moving. So that you can see X in at the bottom. The numerals are a little bit small, but as it deforms, it also moves downstream. So that's one mode of unsteady motion. Let's try it. Let's try another one and get this to work. So this is a slightly different type of behaviour. I guess I need to share this as well.
You should make it full screen.
I'm not sure if that's been shared or not now.
Sure.
Well, okay, for those who can't see it, I'm going to show a static version of this in a second. Again, it kind of sits there, then there's a bit of deformation as it moves, and then it sits there again, and then this just repeats in a periodic way.
Is this with P fixed?
Yes, the pressure differential is fixed. Yeah. Right, so I've lost track of whether I'm sharing or not now. I don't think I am I? Am I back to sharing, Alberto? Okay, thank you. So there we go. So if you couldn't see that a minute ago, this is showing you what was being seen in those movies. The arrows indicating the evolution of time. Okay, but this does seem some way distant from an aerofoil. So let's try and rein ourselves in a little bit and go in the direction we were trying to go in. What we really want is something that looks a bit more like that. So something that at least looks aerofoil shaped in a stream. And the way we're going to set this up is to allow an aerofoil with a finite corner at the back. So traditionally, I guess one uses the Joukowsky transformation for this, which I think, so Paul can correct me if I'm wrong, I think the Joukowsky ends in a cusp at the end. Right, so we don't want a cusp, we want a finite angle, theta c. Okay, so let's start thinking about that problem with no flow. Okay, so we'll put the flow in a bit. So there's our equation again, same equation as before, force balance. But now I'm going to allow the angle to jump at the rear of the cell shape. So basically that means, so theta here, theta is the angle between the unit tangent to the cell boundary and the horizontal. At the trailing edge of my aerofoil, I'm going to allow that to jump. It's best described in a picture, like that. Okay, so that's theta c at the back. And I want to solve that equation as before, same as the Flaherty problem, but with a jump condition for theta at the back of the cell. Okay, so here are some typical solutions to this. So this one is for varying angles theta c. The pressure differential is fixed. You can kind of see it's deforming from a circle into kind of like almost like a pinched teardrop shape, the green one right in the middle. If we fix the angle to be 3 pi over 4 at the back, and then increase the pressure, you can see this trying to deform into a mode 2 type shape, particularly evident with that green boundary in the middle, and then it's just pinched at the back. And you can get mode 3 type shapes as well, which are like the ones I showed you earlier, solving the Flaherty problem, but pinched at one point into this corner angle that we're enforcing. Right, well, what we're interested in is taking such shapes and putting them in a flow. So same problem, let's put them into a flow, and I want everything to be steady now. Okay, so no more unsteadiness, at least as far as this conformal mapping approach is concerned. So there's the problem, uniform stream at infinity, a point vortex as well, introducing some circulation because the lift, and right at the corner, the Kutter condition requires there to be a stagnation point at the corner because it's a finite angle. Okay, so Q, the slip velocity around the boundary has got to be 0 at the corner. So you can solve this problem using a mapping that Adam found that I've not heard of before, called the Karman-Trefftz mapping, and that takes the unit circle in the complex plane into an aerofoil type shape, as you can see at the bottom, with a prescribed angle, prescribed through this parameter, little p. Little p here, nothing to do with pressure. It's this Karman-Trefftz parameter, and you can see theta c in there, the angle that I want to prescribe at the trailing edge. It's not quite as simple as that for us, because we want to allow this shape to deform in response to the flow and to accommodate itself to the flow so I can get a steady solution. I don't know what the aerofoil shape is going to be in advance. So I need to modify this Karman-Trefftz mapping a little bit. So that's what this diagram is showing, and introduce an intermediate mapping plane. So reading from the top left, we start with a circle, then we deform to some shape, and then that shape gets mapped via the Karman-Trefftz mapping to the aerofoil shape with the prescribed corner in the bottom. The colours here, incidentally, are the magnitude of velocity. So these are real solutions for flow past these shapes. That's the idea. Same conformal mapping again. Now it depends on this parameter little p, which is my corner angle. The complex potential as written there. The various parameters are summarized at the bottom. So alpha is, if you like, the flow speed. P is this pressure differential. Not only am I fixing theta c at the trailing edge, but I'm also at liberty to fix what theta is at the trailing edge, which essentially means I can change the angle of attack of this aerofoil shape. And beta, the circulation. So there is circulation now in my calculations. Beta is fixed by enforcing that Kutter condition of a stagnation point at the trailing edge. Right, so here are some calculations done with this Karman-Trefftz mapping. Again, the colours indicate flow speed, So red is high and blue is low. So there's a stagnation point at the leading edge there and also one at the trailing edge. Now what we really want is to be able to increase alpha to a suitable size so that we actually get to something of the order of magnitude of the speeds we expect to see for these unmanned aerial vehicles, like 30 miles an hour or so. What we find is that as you increase alpha, the thing tends to balloon outwards and look less and less like an aerofoil, unfortunately. Something like that. Here are some other calculations playing around with the pressure. So once we got this code working, it was just a question of playing with it to try and construct something that looked a bit like an aerofoil. So there are obvious difficulties with some of these calculations. This one here is not too bad. And then I think there are some other examples. There's another serious problem with this. Not only do these not look all that much like aerofoils at the moment, but the flow speed here is very high, and there it's very low because it's red and blue. If I should do this with the screen. Okay, so the flow speed up here is very fast and then very low there. So the fluid is going very fast along here. By Bernoulli's theorem, or Bernoulli's equation, the pressure is going to be relatively low there and relatively high here. So there's going to be an adverse pressure gradient trying to push fluid backwards along this upper part of the aerofoil. That is going to that is likely to provoke flow separation, which you presumably wish to avoid if you want this to have nice aerodynamic properties. So having got this, this model set up, what we want to do is try and choose the parameters, as I said, to get a realistic looking aerofoil, and we don't want flow separation. So let me just, if it's not clear, maybe not everyone knows about flow separation. Let me just briefly describe what this is. If we relax the idea that we're thinking about an inviscid flow and go to a realistic flow with viscosity, then if the flow speed is high enough, there will be a thin boundary layer at the surface of the shape that we are driving flow over. That's what the red dotted line is supposed to represent, my boundary layer. Now, if you get flow separation, what happens? These are velocity profiles, so the arrows indicating the direction of flow. Flow separation here is occurring at that little part of the cartoon, and thereafter, further downstream, the flow starts going the wrong way, starts going upwards along the aerofoil. Now, what that tends to do is to drag the boundary layer away from the surface of the body and create a large wake with knock-on effects for the drag on your aerofoil. So the summary is that flow separation is bad news, and you want to try and avoid it. Well, to calculate whether flow separation was likely on those aerofoil shapes I just showed you, we solved the boundary layer problem. So we took the boundary layer equations, which are those ones there at the bottom, inputted Q. So Q we got from our inviscid model. That's the slip velocity around the boundary. Input that into the boundary layer equations, and then integrated forwards round from the leading edge, and looked for the condition that flow separation occurs, which is that the shear stress at the wall passes through 0. And indeed, that does happen. So here's one of our sample aerofoil shapes. And the point where there's a red cross, the shear stress is becoming 0, as is indicated by the graph below. And that means that flow separation is occurring, and that's not good. Okay, so what we did next was to take some of these aerofoils and try to see if this is indeed what's happening if we solve the full problem. So what we want to do now is take this cell and put it into a Navier-Stokes flow and see what happens. So we took some parameter values to give us sort of realistic values for these unmanned aerial vehicles. Took one of our deformed aerofoil shapes, excuse me, and put it into GERIS, which is a finite volume code for solving the Navier-Stokes equations, and looked to see what happened. So if this video is going to play, oh, I'm going to have the problems of sharing again, aren't I? So try to share this. The colours here indicate vorticity. So where it's green, the vorticity is well, effectively 0. And what you're seeing here is vorticity being shed off the trailing edge of that aerofoil in the form of a kind of oncoming vortex street downstream. But the take-home message from this is that there's a reasonable amount of flow separation because the boundary layer is really thickening here, as indicated by these colours of the vorticity, and that's something which is not great. I can try and make that statement that it's not great a little bit more concrete. I'll find my talk again. Show you another one. So this is the same aerofoil shape at a slightly lower Reynolds number. This one makes the problem a little bit clearer. So again, all these calculations were done by Adam in Ingeris. You can see the flow separating here on the upward side, in particular of the aerofoil, and then a very large, a large cluster of vortices being shed off downstream. Okay, so this is also not what we're looking for. What we want is a nice.
This was lower Reynolds number.
Lower Reynolds number, yeah. So it's the shape that's causing the problem somehow. Okay. Back on. I'm sharing again. Just to indicate also partly the problem here. This the figure on the left, concentrate on the purple curve rather than the green one. The green one here is showing the drag from those simulations. The purple curve is the lift coefficient as it evolves in time. And if you look at, say, the left-hand picture, which was the higher of the two Reynolds numbers, the lift coefficient is evolving sort of towards 1 here. Now, the actual correct value, if that was a pure inviscid flow with no flow separation, so the boundary layer is behaving itself and staying very close to the surface of the aerofoil, the correct lift should be 2. Okay, so the fact that that's down near 1 is telling us that there's significant flow separation. Right, okay, so what do you try and do about that? It's all about trying to drag this thing into behaving more like an aerofoil. So our next idea was to mimic an idea in the literature, which is to introduce a solid strut at one point of the aerofoil like that. So this is a rigid strut that's going to anchor 2 points of the aerofoil in place. Okay, basically the same problem as before, except now that strut is imposing a force, which I've put in red here. What that means is that the first derivative of the curvature, d kappa by ds, is going to jump at the point of attachment of the strut. And what that means is that the conformal mapping doesn't work anymore. So the Karman-Trefftz approach doesn't work. So what we did instead was we solved, so I'm back to the inviscid flow problem now, okay, not using Ingeris, although we'll get back to that shortly. What we did instead was use the boundary integral method and solve it that way. So that works nicely. I say, Adam did it. Here are some calculations. So these aerofoil shapes, the strut is shown by the broken line. So various flight conditions. The top left one is static, alpha is 0, and then you can see there's various other values of alpha, and CL is the lift coefficient, so the lift that's being generated on the aerofoil. These are all steady state calculations. These do at least look a little bit more like aerofoils. Those, and put them into Ingeris. Let's see what happens. Hopefully something will happen. There we go. Whoops. Sorry, I don't know if I'm sharing this now. I might not be. I'm not. We'll try to. Okay, thank you. There we go. So it's the same two Reynolds numbers as before. This is the higher one. I don't know how good your memory is from what it looked like a minute ago, but this is better than it was. There is less separation now. So this is that solution with a strut put into a Navier-Stokes flow. And if we look at the other one, let's look at the lower Reynolds number now. No way. Ah. Now the lower Reynolds number. And Sasha, I'm almost done. Okay, I know I'm over time slightly. Let me try to share this. Okay, so this is the one with the large number of vortices being shed off the back in the previous example. Now that strut is really holding the aerofoil in place. And okay, so there's still significant flow separation, but it's a lot better than it was. Okay, that vortex street is less wide than it was, for example. One thing I should be very clear about with these simulations is that what we've done is we've solved that inviscid flow problem to get a deformed cell shape, and then we've treated that as a rigid structure put into a Navier-Stokes flow. Okay, so what really should be going on in this simulation is that the cell should be allowed to deform and respond to the viscous stresses being imposed upon it. We were not in a position at this stage of Adam's thesis work to do that properly. Okay, but our idea was if separation is minimized, we can mitigate that as much as possible. Then this should be close to what should happen. It should be close to an equilibrium in which the aerofoil is not changing in time if we have a nice streamlined shape and the separation is minimized. That was the idea. Calculations do need to be done again properly, allowing the aerofoil to deform in response to the viscous flow. And that's pretty much it. I need to go back to sharing the right screen now. This one. So that's just in terms of the lift coefficient, that's what we were looking at before with no strut. When you include the strut, that purple line on the left-hand curve is doing its best to get up towards 2 for you, and it's a lot better than it was a minute ago. And you can play around with where the strut is on the aerofoil boundary and make it a little better again. But it is quite sensitive to what the Reynolds number is as to how well this is performed. So that's the summary of what I've talked about in terms of trying to work towards a model of a deformable aerofoil. And as I say, a major criticism of the simulations I've shown you there, the DNS ones using Jerris, is that they're not true equilibria, and the calculation should really be done for a deforming aerofoil. So we need to do full computations, but I should stop there. And thank you for listening.
Thank you very much. Questions, please. Yes.
One question.
Oh.
Yeah.
So you had the shapes when P was less than 3 and P was greater. I don't do microphones. Normally my voice is loud enough that I go through anything, but anyway, yes. So you've got one P less than 3 and P greater than 3, and that changed the orientation. What happens when P equals 3? You've done the asymptotic analysis for that. Does it just go back to a circle?
No, P equals still deformed. Does it orthogonally, so 90 degrees to it. It's when it's bigger than 3, it will become aligned.
Okay. Yeah. And then the other comment was probably after Adam had finished, I think it was last season in the Formula One, there was massive discussion about deformable tail wings, where they didn't actually design them, supposedly. They weren't supposed to deform, but they just happened to deform. And apparently it made a massive difference. There were just like big legal disputes over this. Yes, absolutely right. Yes, get your patent out on this.
Any other questions? Front of you. Oh.
Yeah. Sasha, can I ask one?
No, just a moment. There is no speaker, is it? You can hear.
Ask a question, please. Can you ask a question?
Oh yeah.
Is it easier to type it maybe?
Shall I type a question, Mark?
I reckon we can hear you now.
Okay. Could you just repeat the question? Switch off mine? No, it's a mute. All the mic. Yeah. Yeah. Everything is muted, and speaker is muted, camera is muted, everything is muted. Thanks. Sorry. Hopefully, it's we can make something. Could you say something? Could you ask a question now? No, it's in process.
If you can start the question, yeah.
Easy. There are no speakers. No? Speaker. Oh my God. Alberto, did you ask a question? No?
Oh no, here we are, it's here now.
Okay.
Have you tried a different sort of boundary map? Oh,
What's that?
what do you mean, Frank?
Can you hear me?
Almost, can almost hear you.
Okay. I mean, either an interacting boundary layer where the pressure responds, where the pressure is free to respond to the boundary layer, rather than imposed from the outer inviscid solution, or a turbulent boundary layer might get you closer to attached flow.
Right. Can you hear me?
Okay. If I could say a bit more.
Yes, yes.
I think the boundary layer you have is bound to separate.
Okay.
And I think that was known by people like Leslie Howarth and others in the 1950s.
Sure.
So it's a long known problem.
Yeah. So I think perhaps what I should have explained is that yes, we realised it would separate. What we were trying to do was push the separation point as far towards the trailing edge as we could.
Okay.
Try and minimise it. So I think you're right. There's no way you'll stop it. The idea was to try and tune the parameters and the shape of the aerofoil to push it backwards as much as possible.
I see. Yeah, that makes good sense. Yeah, yeah. Okay, nice talk, by the way.
Thank you.
Yeah. It seems that it works now.
Oh, does it?
Yeah. So the 100 and then the volume on the top. Thank you, Frank. Any other questions? Yeah. Just no. No.
Hi. So I guess it's going to probably be more of a problem when you have the airfoil able to kind of deform with the flow. But have you kind of do you have any sense of what the kind of tension and the stresses are like in the actual elastic? Of course, you don't want your aerofoil to tear itself apart as soon as it hits any turbulence.
Didn't really look at that in detail. I mean, we can do, the data is there, and the calculation will tell you what the stresses are. I suspect, I mean, I think it's unlikely they're going to be so strong that this is a problem with the thing actually breaking apart. But we didn't actually look at them. So, but that could be done.
Mark, it's possible, right? It's just to continue what you already did, right? So it's not kind of new problem. You can do this using the results of your already calculation of your theory. Yes, yeah. And also you can include membrane stresses. Why not? Yeah. So that is based on that, I mean, continuing this question, are you going to continue this because it's a very interesting topic? Do you think you get support from all PhD students or the?
Very quickly said we switched to the boundary integral method. Okay. But I mean, Adam just did it. This is not a trivial step. So we were lucky with the student.
I was internal, so I remember that. It was very, very good. Yeah, very good.
I think the results.
The topic is very interesting. Yeah, so something should be done definitely. I mean, the further.
It's interesting what Paul said about
adding elasticity to existing, say, wings and yeah, the flexibility or degrees of freedom. Yeah, indeed. Question? Okay.
I'm not sure, maybe I missed that. When you set up the problem, you said that the perimeter of the cell is constant and the area of the cell is constant. So you basically assume that the fluid is incompressible, right?
Yeah, all the way through. Yeah, that's right. Yeah. Including the interior region, that's the critical.
Yeah. It's like inside kind of gas or another fluid, but no motion, no motion.
There's no motion.
Mm-hmm. But just pressure.
Motion, as I said, to try and model some vague way of an aeroplane to have a fluid of different density inside.
Okay. So you are still recording, right? Good. Very good. So yep. Oh, just a moment.
Just to follow on from Dan's question, I think, when you showed the results from the Flaherty paper from 72, you showed that there's these kind of two dipoles, which you get a point of contact and then you get a line of contact. And I think, if I understood Dan's question correctly, it was about the resistance force within that line so that it doesn't effectively snap and you form two independent bubbles or dipoles, I suppose. How do you get from that to maybe the threefold? So you said, I think, that as you increase the pressure, you get this mode 3, etc. But how do you actually? Sorry, maybe I didn't.
It doesn't go through circle mode of contact and then to a mode 3. Okay, so you'd have to do it. So you have to somehow increase the pressure through 3 whilst staying as a circle. And then when you get above 8, the next one, it will snap into a mode 3 shape. So how you'd actually do this in practice is more complicated. Okay, but you're not going through that sequence that you described to get to the mode 3. But yeah, it's a good question. I didn't explain that all that clearly. Absolutely, yeah. As you go through these threshold pressures, all these solutions exist. So once mode 4 shapes have appeared, the 3 and the 2 are also coexisting at the same parameter values.
We finish this seminar. So thank you very much all for attending. Online, it is that we didn't hear a question from John. it's attended. He also our speaker for the next week, Yuri Semenov, he attended as well. His situation in his place is very bad, as you know. So he's from Ukraine, but south from Kiev. So the front line already coming there. He preferred to stay in his place. So hopefully, next week he will make his presentation. So I suggest to do this in the same format, but he will be by Teams that we gather here or in S120, and also to show our support to Ukrainian people in that fight. Okay. So hopefully it will be okay for next week. Yeah, thank you very much, and see you next week.